Hello everyone. Okay, this is mechanics of materials, and then this video, we are going to talk about the simplification of distributed load. And previously we say that if we want to do the simplification of distributed loaded, in the simplification we have two aim or two goals. First of all, finding the resultant force, magnitude resulting force, and the other thing is find the position of resulting force. And previously we had the conclusion is that the magnitude resulting force is equal to the area under the distributed load curve. The area under distributed load curve. Okay, that's the first one. Okay. And the second one is the position of resulting force is just equal to the centroid of the area under the distributed load curve. Okay, and then we spend some time talk about what's the centroid and how to calculate centroid. Okay. Okay, and then we back to the back to the simplification of distributed load. Okay. Okay, so this is example 3.23 in the textbook. Okay, he said there's a granular material. Okay, the granular material, I think this is grade. I'm not sure you see it. I think this is a great shape here. Okay, the granular material exert distributed loading on the beam as shown in 3.58. Okay, this means this graph. Okay, determine magnitude and location of the equivalent resultant of this load. Okay, so simply speaking, it just give you distributed load. Okay, and want you to do a simplification. Okay. Okay, so let's start with it. Okay, for a simplification, our goal is only two. Okay, first of all, finding the resultant force. Okay, finding the resultant force, and we just say what the resultant force is: the area under the distributed load curve. Distributed load curve. Okay, and distributed loading curve is right here. Okay, and it's a trapezoid. Okay, it's trapezoid. So I think I need the Okay, I think I need a white space. Okay, I think I need a white space. Sorry, I think I need a white space here. Okay, so let me redraw the load. Okay, the load is look like this. Okay, the load is look like this. Okay, the load is look like this. Okay. Okay, I'll zoom in the load. Okay, in the left-hand side, the magnitude of the load is, okay, what's the value? Let me see. It's 1500. Okay. Okay, here is 1500. And be careful, it's a unit. 1500 is Newton per meter. Okay, and right-hand side is 750. 700, yeah, Newton per meter. And like I said, this is a distributed load. Okay, this is a load distribution function. So its unit is force over length. Okay, so this is not a force. Be careful. This is a force per unit length. Okay, force per unit length. So it's Newton per meter. So this is not a force. Okay, it's force per length. Okay, or some books say it's a force intensity. Okay, just remind you, it's not a force. Okay, so this is a curve. Okay, and this is 3. Okay, 3 meters. Okay, so first of all, what's the resultant force? Like I say, the resultant force is the area under the distributed load curve. Okay, and this is a trapezoid. Okay, what's the area of a trapezoid? Do you remember trapezoid? Okay, this is a base 1. And I say this base 1 I call A, this base 2 I call B, and you have a height. Okay, you have a height. Okay, what's the area of the trapezoid? Area of trapezoid. In Chinese called 梯形. Okay, what's the area of trapezoid? Okay, base 1 plus base 2 and times h and divided by 2. Okay. Okay, so let's follow this formula. Okay, so the base 1 is 1500. Okay, so 1500. okay, and base 2 is 750, okay, and times the height is 3, and then divided by 2, okay, so you will get the magnitude resultant force. So what's the value? It's 3375. Okay, let me check. Okay, use your calculator. Don't forget, use your calculator. Okay, 3375. 3375, and the unit is Newton. Okay, so we find the first one. Okay, resultant force is 33375 Newton. Okay, that's a resultant force. Okay, and next thing is, where is the position of resultant force? Okay, so after simplification, this will become like this. So I assume this is O here. Okay, after simplification, okay, I think the system will look like this. Okay, here is 3. Here is 3. And resultant force, okay, is point down. Fr is equal to 3375 Newton. And the position we don't know. Okay, I call it X bar. Okay. Okay, we have to determine the X bar is where is the force. Okay, and previously we say, well, the conclusion is the resultant force is located at the centroid of the area under the curve. Okay, so the next thing is, okay, so we have to find what is a centroid. Where is the, okay, I should say where, okay. Where is the centroid? Where is the centroid? Centroid under the low distribution curve. Where is the centroid of a low distribution curve? Okay, where is the centroid? Okay, or more specifically, where is the centroid of the trapezoid? Okay, this is a trapezoid. Okay, where is the centroid of this trapezoid? Okay, so this is not an easy question. Okay, so let me clean up something. Okay, where is the centroid? More specifically, where is the, or in this problem, where is the centroid? Okay, where is the centroid? Centroid of the trapezoid. Okay, so okay, in a previous video in centroid, so if you don't understand the previous centroid calculation, please go back to see the video for the centroid. Okay, I have recorded some video for centroid, so please see the centroid video first, or you don't understand what I'm going to do now. You won't understand. Okay. So what we trying to do now is find the centroid of this trapezoid. Okay, and trapezoid, and in previous video we just introduced the centroid of a rectangular and centroid of right triangle, right? We know that where is the centroid of rectangular and right triangle. For the trapezoid, yeah, of course, if you look up the website or some Google, and I think you can find a centroid formula for the trapezoid. Okay, but I think that's very hard to remember. Okay, but we in previous video I also introduced, if you have complicated shape, we can divide your complicated area into a very small and simple area, and calculate and use them to calculate the centroid of the complicated area. Okay, for example, for this one, what we have is we have a trapezoid shape, but what I can do is make a simpler one. Okay, how to make it simple? Okay, divide it, let it become a simpler shape. How to do that? Okay, so this is, you need some brainstorm for this. Okay, because all we know is rectangular, and right triangle, right? Okay, so that's based on this concept. Okay, if I slice the trapezoid here, okay, so, and then I have area 1. Okay, area 1. area 1. This I call this is area 1, and this is area 2. Okay, so area 1 will become the right triangle. Right triangle. Triangle. Okay, and area 2 will be the rectangular. Right, the rectangular. Okay. Okay, and then so the first thing, if we calculate area, okay, divide them into a very simple area. Okay, rectangular and right triangle. That's very simple. Okay, and then determine the position of each simple area. Okay, determine the centroid of each simple area. Okay, next thing, we have determined the centroid of area 1 and centroid of area 2. Okay, centroid of area 2 is very simple because rectangular. So the centroid of rectangle, I think it should be here. It should be here. Okay, and it's half, and half. That means it's because that means this must be 1.5, right? Because the total is 3, right? Because the centroid of the rectangular must be half, must be right at the half, so this is 1.5, right? Okay, so we are determining the centroid of the rectangular area 2, and then this problem we only consider the x component. So this problem we don't consider y component. Okay, we only consider x component. That's enough. Okay, you will understand. Okay, and then so in area 1, where's the centroid? Where's the centroid of right triangle? I believe it should be here. Okay, and I also believe the position here, I think this should be, yeah, this distance should be 3/3 is equal to 1. This distance must be, yeah, I'm really bad at drawing this right scale. Okay, so but simply speaking, okay, the centroid x component of the centroid of the area 1, the position should be here, and the x component is equal to, should be 1. Okay, 3 divided by 3 is equal to 1. Okay, so that means, okay, that means, that means, okay, then we draw, okay, we have to, yeah, I think I should redraw another one. Okay, that means we can simplify this into the 2 area. Here, okay, and here, okay, and this is 1, and this is 1.5. Okay, and then next things, okay, we determine already determine the centroid of each position. Okay, determine the centroid of each position. And next thing is we have to figure out, okay, we have this position, we have to figure out, use this concept to find out the position of resultant force. Okay, so we need one more step. Okay, here, so here we'll have the FR1. Here is FR. Okay. Right now we have divided the trapezoid into a 2 shape, rectangular and right triangle, and we also locate its centroid. Okay, and then we have to use this information to find out the resultant force. Where's the resultant force, x bar? Okay, so after simplification, okay, and then how to determine the position of resultant force, we have to use the moment balance. And before and after simplification, the moment must be the same. Okay, that's it. So after, if the reference point is here, okay, so let me get rid of this. So after simplification, what's your moment? At the moment, okay, after the moment O and after equal to, okay, FR times X bar, F3375 times the X bar. And in this problem, I make the clockwise is a positive, okay, because I don't want to write so many negative sign, okay. Okay, so and what's the mag what is the moment before simplification? Okay, so before simplification, okay, we did, okay, that's why we calculate the centroid of each area, okay. Okay, so right now, so the before simplification, the moment is FR1 times 1 plus FR2 times 1.5. Okay, and what's the resultant force of area 1? And what's the resultant force of area 2? Okay, resultant of area 2. Okay, okay, what is the resultant of area 1, area 2? Okay, resultant force of area 1 and resultant force of area 2. Okay, that means we have to calculate the area of this right triangle and area of this rectangle, right? Because like I said, in distributing loading, the resultant force is equal to area under the curve. And so the force from the resultant force from this right triangle, okay, it's the area of this triangle. So we have to calculate area of this triangle. So okay, so what is the area of this triangle? Okay, because here is 750, so this must be 750. Okay, so let's solve. Okay, I think I need to get rid of this. Okay. Okay, the FR1 is equal to area under the curve. Okay, area under the curve, area under the curve. So it's 750 times 3 divided by 2. Okay, don't forget this area of this right triangle. And resultant force for area 2 is equal to, yeah, it's a rectangular, very, very simple. So 750 times 3. Okay, so resultant force R1 is 7 divided by 2. So it's 1125, 1125. And this is times 2, this is 2250, 2250. Okay, and then you can just go to insert this value into your equation of moment. Okay, into the equation of moment, and then we have everything here. We only have one variable unknown, or one unknown left. So after you insert this value into this equation, okay, and this one I just also make the same convention, right? Clockwise is positive. Okay, this doesn't affect the answer. Okay, so the x bar will become, okay, I think is let me see, the 1.33. I think it's 1.33. Okay, and unit is meter. Okay, so for the simplification of distributed loaded, okay, the same thing in simplification. We'll find the resultant force and where is the resultant force, and resultant force is just the area under the curve. Okay, that should be easy one. And the second one is determine the position of resultant force. And after simplification, only have one resultant force. Okay, that will make a calculation easier. And the only thing we unknown is the position of resultant force. Okay, we just assume it's in one dimension. Just assume the value is x bar. And then before and after simplification, the moment must be the same. Okay, so we have to calculate the moment before the simplification. And when trying to calculate the moment before simplification, yeah, you need to know the centroid of your area, okay? And since this is trapezoid, okay, trapezoid is the complicated shape, okay? There is a very complicated formula. But we can divide this complicated shape into a rectangular plus a right triangle. And then in the rectangular and right triangle, we can easily identify its centroid position. And then with any centroid position, okay, Then for this one, centroid position for area 2 is here 1.5, area 1 is just 1. Okay, and then we just also have to just go to find the resultant force of each area. Okay, resultant force in each area. Okay, each force of each area. Okay, and then we will got everything, and then put and use the moment balance. We can determine the force of x, the position of resultant force. Okay, so here in this calculation, you will find the geometry is very important. Okay, in this course, geometry very important. You need to how to know the area. Okay, how to know where, and now you need to know where is the centroid of the shape. Okay, so in mechanics of material, geometry really matters. Okay, but in this course, I won't let you calculate very weird shape. Okay, it's a combination of circle and combination of right triangle and rectangular that would cost you a lot of time in calculation. Okay, okay, so here's the so here's the example for the simplification of distributed loading. Also, I just start video here. Okay, so see you in another video. Bye bye.